Okay, so let's do one of these examples from scratch. So we have this proposed reaction mechanism, 2 steps, and what we want to be able to deduce from those 2 steps, some information about the reaction is 1, the net reaction, the overall reaction, which is pretty straightforward, and 2, the predicted rate law. But remember, we want to make sure that the predicted rate law is in terms of the species that are in the net reaction, just like we did in the previous video. So let's take a pause and see if you can at least start the first step, the net reaction step, and then we'll move on. Okay, so the first step is the pretty easy one, which is to look at the 2 elementary steps and identify if you have any intermediate species, which are species that are identical on both sides so that there's no net addition or subtraction of those from the overall reaction. So we just cross those out. That's the green line. The NOCl2 is present on both sides, so we can get rid of that. And then we just add up those unique species on the left and the right sides of the equation. We get this net reaction. So we're done. We know what the net reaction is, and we know what the 2 proposed elementary steps of that reaction. Now we want to figure out what we would predict a rate law to be. So based on what you know so far in the previous example, see if you can come up with a predicted rate law. What's the defining feature in the information that we have right now that would likely be the attributes you would measure experimentally if you were to actually do this in the lab? So the information that we yield here is, what about the rates of these individual elementary steps? We're told the first one is fast and the second one is slow. We've learned that if we have a sequence of fast and slow steps, the slow step is always going to be the rate determining one. And if that's the slowest step, then that's essentially what you're going to observe experimentally, right? The first one's going to go so quick, it doesn't matter, and then this is going to be the one that constrains the overall rate of the reaction. So when we measure the full reaction, that's really the defining characteristic. So could we write a rate law for this second step? See if you can do that. Okay, so we know that for elementary steps of a reaction, the reaction as written can be used to derive the rate law directly. Remember, we can't do that for net reactions because we don't really know the molecularity, how these things are reacting in space, but we can do that for step 2. So we just write this out. I wrote it as rate 2 because it's step 2, and I'm saying that's equal to whatever the rate constant is. I wrote that as K2 because it's the second step, times the concentration of each of those respective species. Okay, so herein lies the problem, the same problem that we saw in the previous example, which is if this is our predicted rate law, because it's the slow rate determining step, notice that it contains a species that is not contained in the actual overall reaction. That is an intermediate that we've crossed out. And so we need to figure out if we can get this predicted rate law in terms of just the reactants in the overall reaction, the thing that we would actually be mixing together in the lab. We, remember, don't know that NOCl2 exists if we're just mixing these 2 species together. There's nothing about the balanced reaction in blue here that tells us that. So could we get this in terms of NO and Cl2? Well, the first step is probably to write out the other information that we have, which are rate laws for the first reaction. But notice that this has this double arrow here that implies that this is a reversible reaction. So we could actually write up a rate law for the forward and the reverse reaction. So see if you can do that. Okay, so we have this first elementary step. I just added rate constants K1 and K inverse 1 here because this is a reversible reaction, and then I wrote out the corresponding rate laws as we've done many times before. The nice thing is we can see that the reverse reaction here is in terms of NOCl2, that is that intermediate species that we want to somehow substitute and replace from what our rate limiting step would be. So just like we did in the previous example, if we've got this double arrow, this is super fast, so we can assume this step is at equilibrium, which just means that the forward and reverse rate are equivalent to each other. The reaction is happening in forward and reverse directions at the same exact rate. That has consequences in terms of these rate laws because that allows us to set up an equality and make them equal to each other. So if rate 1 is equal to, that should be rate minus 1 here, then we can set up this condition that we have an equivalency, and we have that written down here. So Now we can solve for NoCl2 and try to pop that into the equation to get rid of that. So remember, we can get to a rate law that is in terms of just the overall net constituents of that reaction. So a little algebraic substitution. Now we're solved for NoCl2 and we can go ahead and try to substitute that. So let's go sub that and rewrite that expression. So that looks something like this. Go ahead, make sure you write this out and you've convinced yourself that that is true. Notice now that we have the entire rate here in terms of NO and Cl2 and constants. That's the goal here. We've got two NO terms on the right, so we can collect those and then raise that to the second power. And what we get is this final form. That is the predicted rate law, because it is now in terms of NO and Cl2, but remember the origin of this whole thing was based on the original intuition that this was the slow step, so we wrote out the rate law for the slow elementary step. We couldn't stop there simply because that rate law was in terms of an intermediate species that doesn't actually exist in the overall reaction, so we had to do a little bit of fancy footwork here with the first step to make sure we could do some substitutions. But now we're in a good form, so the overall rate that we would predict for this reaction would be third order, it'd be second order in NO, and first order in Cl2.